Hello. So everyone, okay, so today we're going to talk about kinematics. We're going to talk about equations of motion and kinematics. So yes. Okay. Has everyone found the assignment? The second assignment for physics. Have you found it? Is there anyone here who doesn't know where to find it? Okay. So that is absolutely fine. I'll share my screen. If you go to the COMPOS website, so you type COMPOS and in get involved assignments, here they are. So year 12, assignment 1, 2, assignment 1, 2. So physics, we're doing 1202 today. This is the equations of motion. It is due on the 12th of November, so you have 3 weeks to do it. Does that sound right? Yeah, 12 weeks to do it. Sorry, 3 weeks to do it. And yeah, so that's that. Hope that helps. Okay, so we are talking about equations of motion, and so I understand that some of you haven't seen it. I have done at least 2 webinars on this topic. So if you go back to our webinars, so if you go to YouTube and your channel, you can find the playlists. Okay, so we have the year 13 webinars, the year 12 webinars, year 10 webinars, and COMPOS webinars is also year 12, so you can watch these as well. So you can watch COMPOS webinars and COMPOS year 12 webinars. And here's the link, just in case. So I've covered this topic quite thoroughly in previous webinars, so it never hurts to do some extra stuff. So today we're going to talk about what is an equation of motion, what is a relative velocity, and we're going to do some projectile motion examples as well. So let's start. So first of all, mechanics, mechanics and kinematics. Let's do some definitions. So mechanics is a study of motion, of course, and kinematics is a particular area of mechanics. Kinematics studies is a study of how the objects move. How objects move. And dynamics, we will do dynamics in the next assignments. Dynamics is a study of why objects move. So in kinematics, we study displacement, acceleration, etc. In dynamics, we study forces, because force is a reason of something moving. Okay, so these are subtopics of mechanics. So mechanics includes kinematics and dynamics, and also other stuff, but this is the main two. Okay, the main purpose, main purpose, let's make a purpose of mechanics is to know the position of an object at any given time t. Any given time t. And the function that tells you the position, rt, so r is a vector of t, is the position vector of the object at any given time t. So basically, r of t, we'll get to r of t. We'll talk about r of t later on. But r of t tells you the position of an object at any given time. So it answers the main. It is the main purpose of mechanics. So RT is mechanics, and it's a pity that R of t is not studied thoroughly in the school syllabus, because it's kind of it's an omission. I've never heard the name for the fourth, fifth, and sixth spatial derivatives, Neil. I'm not sure. I never used them, and I can't see why somebody would use them. It's the rate at which the acceleration of the acceleration of the acceleration changes, which is like, well, okay, too complicated. Like, right. Anyways, the position of the at any given time t. So, for example, at t equals 3, you are at point 2, 4. Yeah, so in 2 dimensions. So you can write, hence, r of 2, oh sorry, 3, at time equals 3, your position vector is 2, 4. This is what it means. So position vector of an object. So it tells you your position at any given time. So it's not rocket science. Well, not necessarily rocket science, because you can talk about rockets. But anyways, it's not that complicated. It's a vector at any given time. Okay. Lighting on buildings with their greater rate of change. Oh, interesting. Lightning on buildings. That is fascinating. No, unfortunately, I'm unfamiliar with the topic, Neil, so I can't be of help here. Okay. So problem 1. Find the relative velocities of the plane, train, truck, helicopter, girl. So basically, we are talking about frames of reference. Frame of reference, and this is important because we will study frames of reference in later on. A frame of reference. Is a set of clocks and rulers that you can use to measure distance and time, distances and time. Basically, so I'm in my room, and I have rulers. Basically, this could be my x-axis. This could be my y-axis, this could be my z-axis. I can measure my position relative to the objects in my room, or relative to my room. This is my frame of reference. Okay. To me, this frame of reference is not moving. But if you think about it, the Earth is moving, so it is moving. So with respect, when I'm concerned, I say this is stationary. And if something is moving, it is moving, right? This is moving relative to my room. So yeah, that's relative motion for you, and relative velocities. So to understand relative velocities, I've drawn up an example. So let's say you are in the plane, and relative to you, the plane is not moving, because if you're in the plane is moving at 0 meters per second. 0 meters per second. That's understandable. Okay. If you're in the plane and you're looking at the helicopter is moving, let's say right is positive and left is negative. So the velocity of the helicopter relative to you is plus 250 meters per second, because it's moving right at 250 meters per second. If you're in the train, sorry, no, that's not how I intended it to be. If you are in the plane, the speed of the helicopter is plus 215 meters per second. The speed of velocity of the train. If you're on the plane, the train is moving to the right. Okay, if you're in a plane, you look down at the train is moving backwards relative to you at 170. So it's plus 170 meters per second. Does that make sense? Relative to you, the train is moving to the right at 170. If you're in the plane and you're looking at the train is moving backwards. Does anyone have a question on that? Any problems? Okay. Silence. The girl on the bench. So this is the girl on the bench. And if you are in the plane, it looks like the girl is moving towards you. The girl is moving towards you at 200 meters per second. So it's plus 200 meters per second. And the truck is moving at 210 meters per second. Does that all make sense? Anyone? Is there anyone who doesn't understand? If you're in the helicopter, the plane is moving to the left, so it's minus 250 meters per second. The helicopter is not moving because you're in the helicopter. The train is moving at minus 80 meters per second. The girl is moving at minus 50 meters per second. The truck is moving at minus 40 meters per second. It's because it's moving left. If you're on the train, the plane is moving at minus 170 meters per second. The helicopter is moving at 80, plus 80 meters per second. You can notice the symmetry, by the way. The train is not moving, so meters per second, 0 meters per second. The girl is moving at plus 30 meters per second, and the truck is moving at plus 40 meters per second. If you are the girl, the plane is moving at minus 200 meters per second. If you are, the helicopter is moving at plus 50 meters per second. If you are, the train is moving at minus 30 meters per second. The girl is not moving, and the truck is plus 10 meters meters per second. So that's going to be minus 10 meters per second. This is 0 meters per second. Okay, so this is 40 minus 40 meters per second. If you are in the truck and the helicopter is moving at plus 40 meters per second. Oh, wait a second. If you are in the truck, the helicopter is moving at plus 40. If you're in the truck, the train is moving at minus 40. Oh, okay, that's fine. If you're in the truck, the airplane is moving at minus 210 meters per second. Okay. Right. Measuring the impact of lightning. Light doesn't adhere to the idea of reference frames. Of why? Oh, because it's an electric field. It's an electric field propagating through space. You can't have. Imagine you are in a very fast boat and you drop a tennis ball into the water. Let's say water waves are 2 meters per second. So it's why light does not adhere here to reference frames. This is the first thing that came to my mind. I'm not saying that this is the definition, but this is how I understand it. So light is a wave, right? We're assuming that light propagates as a wave. So imagine you're on a boat, and the boat is moving at 10 meters per second. If you have another boat which is stationary, 0 meters per second. 0 meters per second. If you drop a tennis ball from a stationary boat into the water, you will have ripples on the water that propagate out at a speed of 2 meters per second. Let's say. Now, if you drop a tennis ball from a moving boat, the waves don't start propagating at 12 meters per second. It propagates still at 2 meters per second. Because light is a propagation of a wave through space, it doesn't depend on whether you're moving or not. It will propagate at the same velocity. Now, if you want to ask why it can propagate inside your spaceship, then I don't have an answer for you at the moment. But hopefully that makes sense. Does this explanation make some sort of sense? It's a very basic view of things, but they would, of course. Yeah, I'm not saying that this is an example, but for different observers, it will still. But that's one of the if you think of light as a disturbance of the electric and magnetic fields, it has a set velocity at which it travels, and it doesn't ask you whether you're moving or not. Okay. Would the waves not appear to? They would, yes. How is the light not breaking the speed of light relative to its previous position, which you measured its velocity from the reference frame? Break the speed of light. No, light doesn't break. Light doesn't break the speed of light. Like even light, nothing can travel faster than light. Okay, I'm not ready to go into that. Okay, this is not the topic. We're doing classic mechanics where reference frames are very strict. We're using ideas from Newton, and we're using ideas from Galileo. So he was sort of the first one who thought of these. Okay, so low speeds. Problem 2. A runner wants to complete a run with an average velocity. So this is a question which is commonly asked at job interviews, such as Google, for example. I think this particular question was from a Google job interview. A runner wants to complete a run with an average velocity 10 meters a second. Average speed, sorry, of course. Average speed. Use the average speed. He runs half the race at 5 meters per second. How fast must he run the remaining distance? Mohammed, you didn't put your name or ID. Do you know your your name in Google Classroom? Just write a comment in your submission. Just write a comment who you are, so we can identify you, or just drop me an email. Drop me an email at compos@physics. Compos@physics. UK. Drop me an email so I can identify you. Okay, perfect. Does anyone know the answer for question 1? It is a popular question. You can guess. Can you give it a guess? How fast? 15. Definitely not 15. Very good. Neil understands that the answer is not 15. That's good. Okay. Well, I mean, it's a good guess. Like, I mean, you would guess 15. So let's make it like a proper race. Let's make it what? 1,000-meter race. Let's say the distance is 1,000 meters. So expected time. He's expected to spend 100 seconds on the race. 100 seconds on the race. How many has he already spent? Time spent. How much time has he already spent? He ran 500 meters, remember? Ran 500 meters. Well, you can do that. I mean, no, he ran 500 meters at 5 meters a second. Not 2,500, 100, yes. So he ran 500 meters at 5 meters per second. So he already spent 100 seconds. So obviously it can't be done. It's impossible, of course. He spent all the time possible. No matter how fast he runs, he will never be able to make his average speed 1,000. So yeah, this is a popular question with interviews. And the second part of this question, runners say you always run slower on a windy day. And it is true. And explain why. What? Sorry. Oh, the running slower on a windy day. Well, yeah, that's what I'm trying to explain. Well, Charlie, that's a good point. More work has to be done against air resistance. But I mean, if you're running a lap, you're going with the wind, and then you're going against the wind. So it's supposed to average out, right? Because you run half the distance when the wind is helping you, and you run half the distance when the wind is working against you. So it seems like it shouldn't affect, because imagine the wind is blowing this way, and when you're running this way, the wind is helping you, and when you're running back, the wind is not helping you. But that would be true if it took you equal time to run this distance and this distance. But it doesn't take you equal time. Imagine you're running this in this direction with a speed v is your own speed, plus u is the speed at which the wind helps you. And this is your speed minus the speed that you lose because of the wind. So for example, let's say the wind adds or subtracts. So you run at 4 meters a second, 4 meters a second. And when you're going to the right, the wind helps you by 1 meter per second. And when you run back, it's 4 meters per second minus 1 meter per second. In this case, we can use something called the extreme case scenario. The extreme case scenario, extreme case analysis. Extreme case analysis. What would be the extreme case for this example? Can somebody think of an extreme case for this example? Yes, if u equals v. So let's just let me just tidy this up a little. So that is question 1. Assume race is 1,000 meters. And this is the second question. Extreme case would be u equals v. That means in this case, when you're running this way, when you're running with the wind, your speed is 2v, and when you're running back, your speed is 0. So you can't even finish the race. Your time is equal to infinity. You will never win. You will never beat the speed that you normally run with. So your normal time is the distance divided by v, right? With no wind. With wind, wind, you run half the distance, so S over 2 divided by V plus U, and you run plus S over 2 V minus U with wind. So this is your time with no wind, and this is your time with wind. So distance divided by time. So half the distance divided by the fast speed, and half the distance divided by the slower speed. And let's simplify that. I haven't done this before, but so you multiply these together. So S over 2, and you have 1 V plus U plus 1 over V minus U. Find the common denominator. So S over 2. So it's V minus U plus V plus U divided by V squared minus U squared. U cancels, and that's going to be S multiplied by 2V divided by 2V squared minus U squared. And so it's going to be S multiplied by V divided by V squared minus U squared. Does that help? We compare with S over V. Yes, we can. So in the normal time is S over V, which you can also simplify as S, not S simplify, but write it as, sorry. And the time with wind is SV over V squared minus U squared. Can you tell me which one is bigger and which one is smaller? Practice your skills. The bottom one is always bigger. Yes. SV over V squared minus U squared is always bigger. Always bigger than SV over V squared. Yeah, that's it. And if U equals V, then this becomes infinity. If U equals V, this becomes infinity. So that's always bigger. So here we used the extreme case analysis, which gives us a quick answer. And here I use the algebraic approach. So the brute force method. So algebraic. So this is the proper approach. The proper approach, sometimes it's too long and you don't need it. So you need to be able to use both. You need the extreme case analysis. So in complicated questions, you just ask yourself, what would happen if we take this to the limit, to the very extreme? Oh, it's that. Okay, so and then you can work from there. Okay. Okay. So somebody was asking a question. The PDF I uploaded for Math 1 shows. Email me, please. Okay, email me explaining what happens, and yes. Okay. But be brief if you email us. Just stick to the point. This has happened. This has happened. This has happened. Please, could you fix that? We just yes, straight to the point. Okay, so we started our session with discussing the position vector of an object at any given time. So this is what we're going to do in problem 3. Make SUVAT better. So what does it mean? Well, what is an equation of motion? So I've went through this in the assignment. So you know suvat, you know your suvat, so you have u plus at. We have s equals ut plus 1/2 at squared. Then we have s equals u plus v over 2 times t. And we have v squared equals u squared plus 2as. So these are the 4 equations. 2 of these equations I like more than the other 2. I like the first 2. The first 2 are because they're really cool. Because they're really cool in terms of because they depend on t, right? So the first 2 only depend on t and the initial parameters. I'm going to upgrade these. I'm going to say that this is velocity as a function of time. It's velocity versus time. It's a function because it gives you the velocity at any given time is equal to the initial velocity plus acceleration multiplied by time. Okay? But velocity is a vector. And this is a vector. And this is a vector. So this is a proper Suvat equation. Okay? I'm going to make this. Displacement. Displacement is a vector. And it's equal to the initial velocity, which is v0 t, which is also a vector, plus 1/2 acceleration multiplied by t squared. Now, s, the displacement, s, is also known as delta r, is the change in position of an object, which is equal to the current position of the object minus the initial position of the object. The current position, the current position is the position at any given moment in time. So this is the current position. And this is the initial position. Because the change in displacement is final minus initial. So current position or final position minus initial position. And the current position is r of t minus r0. So we can stick that into here, and we can rewrite it as r of t minus r0 equals v0t plus 1/2 a t squared. In other words, r of t is equal to r0 plus v0t plus 1/2 a t squared. And we can go further with this. What is r of t? Well, it's a vector. What is a vector? Well, vector has coordinates. We can write it as the x position and the y position. This is a vector. Is equal to initial position plus velocity, the initial velocity in the x direction, initial velocity in the y direction times t plus 1/2 acceleration in the x direction, acceleration in the y direction, t squared. And then we can write the top line and the bottom line separately, and we can say that x of t the position of an object, is the initial position plus the initial velocity times time plus 1/2 acceleration in the x direction times t squared. So we came back sort of from where we started, because this is the Suvat equation. It's just a modified version. And y of t and is y0 plus v0 yt plus 1/2 a yt squared. So this gives these are equations of motion. Why is it important? Why is this such a big deal? Why am I spending time on this? Because if you know time, you know x and y. You know the position of the object at any given in time. You know the x position and the y position at any given moment in time. So if you know time, you also know x and y. You know if you know when, you know where. And this is called an equation of motion. So an equation of motion gives you the position of an object at any given moment in time. And this could be written in this form. This is the brief version. This is the vector form. And this is in the component form, or whatever you like to call it, parametric form, component form. Okay. Any questions? Any questions? Is it? So what we did is we took the second Suvat equation and we started playing around with it. There's also a neat way of getting the Suvat equations, and I'm going to show you. Well, before we do that, let's practice a little bit with this. So an object is moving according to the equations. X of t is 2 minus 5t plus 4t squared. Y is 7 plus 12t minus 3t squared. And if you compare that, well, okay, let's do that. So find the initial position. Well, initial means t equals 0. When t is 0, so x of 0 is 2 minus 0 plus 0, so 2. And y of 0 is 7 plus 0 minus 0, so that's 7. So the initial position, you could say x is 2, y is 7. Or you could say the r0, the initial position, is 2, 7. Does that make sense? Or how do you understand this? On a scale of 0 to 10, please vote in the chat. You understand on a scale of 0 to 10, please? 989. Okay. The initial position, so the initial coordinate. Okay, very good. Initial velocity. Well, there are different ways how to do this. But you can look at this. You can look at these equations. And you can look at these equations. The initial velocity, that's this one. The initial x velocity is -5. and the initial y velocity is 12. So the initial velocity is a vector minus 5, 12. Position 2, 7. Initial speed. Who can tell me the initial speed? What's the initial speed? The initial velocity is minus 512. What's the initial speed? 13. Oh, very good. That's very quick. 13 meters per second, of course. And the acceleration. And the acceleration is, well, it's 1/2 a. So it's 1/2 of that. So it's 8. Acceleration in the x direction is 8. And the acceleration in the y direction is minus 6. So acceleration is 8 minus 6 meters per second squared. This is meters per second. And this is meters, of course. And the modulus of the acceleration, initial acceleration, is, well, 10. 10 meters per second squared. The acceleration is 10 meters per second squared, but it is a vector with components 8 and 6, right? So I hope that makes sense. Hope that makes sense. For these vectors, would you give the answer as a vector or find the magnitude and direction? It depends on what it is asking you to find. If it's asking you to find the magnitude and direction, you find the magnitude and direction. If it's not specified, yeah, vector is good. Okay. Okay, so we sort of explored this in a bit. So let's obtain the same equations. Let's obtain the Suvat equations from calculus. Where does use calculus to obtain Suvat? So let's say acceleration is a constant vector. That's wrong. Technically that would be const like this. It's a vector. But yeah, let's assume you assume you understand what I'm talking about. Acceleration is constant. We know that velocity, acceleration is the derivative of velocity. And we know that the velocity is the derivative of displacement, dr dt. Okay. I'm going to multiply both sides by dt. So a multiplied by dt equals dv. And I'm going to integrate. So I'm going to draw the integral. And well, when we integrate, we have a constant. So this is going to be at, because acceleration is constant. We can take it out. Dt is equal to integral of dv, yes. And this is going to be the integral of dt is t. So a t equals v. Now I'm supposed to write plus c here, but I'm it doesn't matter which where I add the plus c, so I'm going to add it here. Plus c. Okay, plus c is a constant. So what I have v, which is at plus c, and what is c? Well, when t is 0, v is equal to c. If t is 0, v is equal to c. Therefore, c is the initial velocity. So we have v equal to at plus v0. We can rewrite this as v is a function of t is equal to v0 plus at. Ooh, so we got the first Suvat equation in vector form, of course, because now we are grown-ups. Don't worry if you don't fully understand that. This is not what we're doing. This is just here to help you. Right, now we can replace, we can use this in here. So we can write v0 plus at is equal to dr dt. Yes, there will be a c on both sides, but having c on both sides, it doesn't matter if, look, imagine you integrate x squared dx equals integral of x cubed dx. You can write, so this is going to be x cubed over 3 plus c1 equals x to the power 4 over 4 plus c2. You have two different constants, of course. But if you move c2 to the left or to the right, it doesn't matter which way you move it. Let's move c2. It's going to be x cubed divided by 3 plus c1 minus c2 equals x to the power 4 over 4. Substitute c equals c1 minus c2. And then you got x cubed over 3 plus c equals x4 over 4. You're allowed to get rid of one of the constants because it's an arbitrary constant. Okay. Why c on one side only? And if you make a silly mistake, you forget to write 1 and 2, then you cancel them out, and then you're in big trouble. Okay, so don't do that. Don't do that mistake. Okay. Right, so I'm going to multiply by dt. So v0 dt plus a t dt equals dr. And we integrate. So here v0 is a constant because it's the initial velocity. It doesn't change. It doesn't depend on time. So v0 integral dt plus a does not depend on the initial, depend on time, doesn't change with time. So it's t dt. And it's this one is dr. So it's going to be r Okay, it's going to be r, and here it's going to be v0 t plus the integral of t squared over 2. Yes, so it's a multiplied by t squared over 2 plus c equals r. So we can rewrite this r equal to v0t plus 1/2 a t squared. You see where I'm going with this, yeah? Plus c. And plus c, well, it turns out when t is 0, r is equal to c. That means, therefore, c is the initial position. So we get r of t is equal to r0 plus v0t plus 1/2 a t squared. Beautiful. How does integration work? We are going to study integration, so don't worry if you haven't done integration yet. Don't worry. Okay, it's in so after this. So this topic is trigonometry. Then we do differentiation, and then we do integration. So we'll study integration at its finest in a few months. Okay, so don't worry if you haven't done it. I'm just showing you that you can obtain the SUVAT just from this. Just from this, you can obtain SUVAT. So SUVAT doesn't come out of nowhere. Sometimes make you think that in school when they give you equations, the equations come out of nowhere, but they never do. They never do. Okay, so let's move on. What time is it? Oh, 7 o'clock. Wow. A material point is moving with initial velocity 6 meters a second with acceleration 4 meters a second at 120 degrees to the initial velocity. Find the displacement after 3 seconds. Interesting. So this is where we can practice our knowledge. So let's just break it down. So we have a particle which is moving 6 meters a second. So let's assume it is moving. It doesn't specify which way it is moving. So assume it's moving to the right. The initial velocity is 6 meters a second. And immediately I can write it as a vector, 6, 0. So assume moving along x axis initially. Because what happens next? Acceleration is 4, but it's not along the x-axis. It's 120 degrees to the velocity. So the acceleration is in this direction. This is the acceleration. Okay, who's going to help me to find the components of the acceleration? We do partial differentiation or in year 13. So as a matter of fact, if you go to this one and you download maths 1302, which is coming soon, I'm still proofreading it, but it's gonna come out probably tomorrow. It has partial derivatives in it. 4 cos 120, 4 sine 120, very good, thank you. And cos 120 is minus a half. So this is going to be 4 cos 120 and 4 sine 120, which is minus 2. and 4 square root of 3 over 2, so 2 square root of 3 meters per second squared, meters per second. It doesn't say where the object is, so we assume that the initial position is 0, 0. 0, 0. That means R0 is 0, 0. Okay, so we write our wonderful equation of motion. So R of t is equal to R0 plus V0t plus 1/2 AT squared. So R of t is equal to R0, which is 0, 0, plus 60 multiplied by time, plus 1/2 multiplied by minus 2 root 3 multiplied by t squared. And what are they asking? They're asking for the displacement after 3 seconds. Okay. At t equals 3, R of 3 is 0, 0, plus 6 times 3, so 18, 0, plus minus 1 times 9, minus 9, and square root of 3 times 3 times 9, so it's 9 root 3. So it's going to be 9 root 3. Therefore, answer. Displacement is a vector, is equal to 9 root 3. At 3 seconds, t equals 3, the object is at point 9 root 3. And of course, in the spirit of this question, they're asking for the modulus of the displacement. So it's what, 9 times 2, so 18 meters. How do you find the components of the acceleration? Yes, I resolved the vectors. We did this in the previous assignment. Yeah. So this is the x-axis. So this is the y-axis, and this is the x-axis. So x-axis and the y-axis, and the formula for resolving vectors is 4 cos is the modulus. The modulus is 4. 4 cos of 120 is 4 sine 120. Okay, and that. All right. So this is the vector form of doing it, and I think it's the best way of doing it because, well, yeah. So this is a more advanced approach, and I urge you to practice it a little bit. Okay, so problem 6, we are shooting from a cannon, and we're shooting at from a height of 0 meters at an angle of 60 degrees, and the speed is 20 meters per second. I'm going to show you how easy it is when you're using vectors, because you need to know the acceleration. Acceleration is acceleration is 0 minus 9.81. That's how acceleration works, because it's downwards. Initial velocity is 60 degrees, so it's 20 cos 60 and 20 sine 60. So the initial velocity is 10 and 10 root 3. Okay, good. That's very good. So the question is, find the time. Okay, so we write down the equation. The time here, of course, we're interested in this time. So we write down position r of t is equal to the initial position, and this is 0, 0. So it's 0, 0 plus the initial velocity. So it's 10 root 3 multiplied by t, and plus the acceleration plus 1/2 acceleration, 0 minus 9.81 multiplied by t squared. And remember, they taught you that horizontal movement and vertical movement are independent. So we split them into components. So because we know that this is x, y, so we have x is equal to 0 plus 10t plus 0 t squared, and y is equal to 0 plus 10 root 3 t plus 1/2, or minus 1/2 times 9.81 t squared. That is beautiful, because now you can find maximum. Well, we can find the t, we can find the time. Yeah, there's an acceleration due to gravity. It's a given. And here we have when it lands, y is 0. So we have y, which is 10 root 3 t minus 1/2 multiplied by 9.81 t squared. So we can, and this is equal to 0. We can solve that for t. So t is equal to 20 root 3 divided by 9.81, which is 20 root 3 divided by 9.81. 3.53 seconds. 3.53 seconds. This is the time it takes for the object to land. T is 3.53 seconds. It takes half the time to reach the maximum point. So the maximum point is t equals half of that. So divide by 2, 1.77 seconds. All right. And then we do position. Position at t equals 1.77 seconds. And this is r of 1.77. And that's equal to 0, 0 plus 10 root 3 times 1.77 plus 1/2, 0 minus 9.81 multiplied by 1.77 squared. And that gives us times 17.7, which is 17.7. And, well, that would be 0. This is the maximum height. So the maximum height is 17.7. So position at t equals 3.53 seconds. We just substitute 3.53. So you can see how powerful this tool is. Because, I don't know, well, I can give you an example. I once a friend came up to me and said, "Let's make a game for iPhone," and I said, "Ah, hell yeah, let's do it. Let's make a game." And it was a spaceship which was traveling in a parabolic trajectory. Anyways, I used this because this is exactly how I modeled my spaceship in the game. So I used it. I used it to create a game. The game never got published because we were lazy. But anyways, it was a nice experience. It would have worked if yeah. And here you do the same thing. It's 0, 0 plus so it's going to be 10 root 3 multiplied by 3.53 plus 1/2, 0 minus 9.81, 3.53 squared. That should give you, oh, sorry, that's not, doesn't make any sense. No, it doesn't make any sense. This is 0. This is, sorry, the range, that's not 70.7, that's the middle position. And the height is 10 root 3 multiplied by 1.77 minus 0.5 times 1.77 times 9.81, 21.9, so 22.0, 22.0. So maximum height is 22.0 meters. So we have found the time, and now we need this. So this gives us 10 times 3.53, so 35.3 meters. 35.3 meters, that's the, so the range, L, is 35.3 meters. Okay. And now my favorite part, we actually do the experiment. So we have the cannon, 0 meters tall, and 60 degrees, and 20 meters a second. And we predict that it will land 30, how much? 35.3 meters. 35.3 meters. Zoom in. And let's shoot a piano. Okay, and slow motion, and shoot. Bam. Okay, so and now you can measure the distance. The range is 35.3 meters. That's true. The time, it took 3.53 seconds, indeed. And the maximum height is, ooh, we're off. We're quite significantly off. I'm not sure what happened there. 10 root 3 multiplied by 1.77 minus 0.5 times 9.81 times 1.77 squared. Yeah, 15.3. Okay. 15.3. 15.3 meters. 15.3 meters. Yeah, I forgot this is 1.77 squared, indeed. Okay, so yeah, you see that, and you can you can use all sorts of things to model it, and yeah, you can you can use a spreadsheet to model it. You can yeah. So the other one. Would you like so would you we have time to do one problem. Tell me whether you'd like to do problem 7 or problem 6b. 6b is another one. And with different parameters, and we'll do problem 7. It looks like problem 7. Okay. An object is thrown up the slope, and thrown up the slope at an angle of 60 degrees with velocity 20. How far up the slope will it land? So basically, we're shooting, and it will hit the slope at some point. So it's sort of the same thing. It's just we need to find where it hits the slope. Well, you can use the equation of motion here. Equation of motion. So let's do it as a computer would. So equation of motion. Equation of motion. Well, we have R, which is equal to, I'm dropping the T here because, we start from 0, 0. So assume we start from 0, 0. This is the x-axis, and this is the y-axis. Y-axis. This is 30 degrees, right? So if it's 30 degrees, does anyone know the equation of this line? It's the equation of a straight line. What's the gradient of this line? Yes, Charlie, exactly. That's exactly what I'm doing. 2 over root 3, 1 over root 4, 3, 1 square root over square root of 3. Yes, Charlie, it is 1 over square root of 3. The gradient of this line is the tangent. The tangent is the gradient of a line, and the line in the gradient is a tangent. So it's y equals 1 over square root of 3x. That's the equation of this line. And now we're going to use coordinate geometry to find the point of intersection. Okay, so r is for the object of the object is going to be 0, 0 plus the initial velocity. Initial velocity is 20 cos 60, 20 sine 60 multiplied by t minus 1/2. I'm going to use 0 minus 10 for g, just to make it simpler for myself. And multiplied by t squared. And this is x. This is x and y. This is x and y. So we have x is equal to 20 cos 60 t. Well, that's 10. 10t. 10t minus 0. Well, x is 10t. Y is 20. It's 10 root 3. 20 sine 60 is 10 root 3 t minus, sorry, plus minus 5t squared. And the third equation, we know that it crosses the line, so y is equal to 1 over square root of 3x. Oh, that's nice. So we can use t equals x over 10. and y is 1 over square root of 3x, which is 10t. So it's 10t divided by square root of 3. Oh, okay. So we put this into here, and what do we get? We get 10t divided by square root of 3 is equal to 10 square root of 3t minus 5t squared multiplied by square root of 3, so 10t equals 30t minus 5 square root of 3t squared. So 20t is equal to 5 square root of 3t squared. Well, t is not 0, obviously. It doesn't take 0 time to reach, so we can divide by t because t is not 0. And therefore, 20 divided by 5 is 4. So 4 divided by square root of 3, and that's equal to time. So time of impact is equal to 4 square root of 3 over 3. Okay. So at time of impact, the position of the object, the position at 4 square root of 3 over 3 is, well, 0, 0 plus 10 over 10 root 3 4 root 3 over 3 plus 0 minus 10, so a half minus 10 multiplied by 16 thirds. Well, t squared is 16 thirds. And we simplify that. 10 40 root 3 over 3, 40 root 3 over 3. And here we have 3 that cancels, and that's 40. Plus, and this is over 2, that's 5. 5 times 80 over 3. 80 minus 80 over 3, 0. So that's 40 root 3 over 3. And 120 minus 40 over 3. Minus 40 over 3. And that, well, looks like it is 80 over 3. The question is how far. So how far, that means we find the modulus. So this point, the point of where it crosses is going to be, is this. Because that's where the object is. The beautiful thing about the equation of motion, because it tells you where the object is at any given time. We found that the time is 4 square root of 3 over 3. We found that this is the point where it touches, where it hits the slope, and we need to find the distance. And the distance is the modulus of r. And we find the 40 square root of 3 over 3 squared plus minus 40 over 3 squared square root. And I believe this to be 80 over 3. Correct me if I am wrong. It's 80 over 3. 80 over 3 meters. Because acceleration is downwards. Acceleration is g. And g is minus 10 meters per second squared. So in the x direction, it is 0, and then in the y direction is minus 10. Acceleration is, which acceleration as a vector is 0 minus 10 meters per second squared. Well, it is, but we are assuming we are rounding up to 10. it is perfectly suitable. Like, I mean, if it doesn't say use 9.81, in our assignments, use 10 by all means, okay? I want you to use the calculator less, basically. Because with 981, you always need a calculator. With 10, look, I've done it, and I didn't need a calculator. Yeah. So yeah, that's how you do it. I mean, you could use a different method. You could use a different method here. You could say, well, let's go into the frame of reference of the so how I would do it here. I would say this is the slope, and this will be my x-axis. And the perpendicular to that is my y-axis. Y-axis. And I'm shooting at 60 degrees. Shooting at 60 degrees, and it hits the ground somewhere here. And the acceleration is this way. Acceleration is this way. I don't really like this picture. So what do I do to it? Like any reasonable person would. Like any reasonable person would. I'm going to take this picture. Take this picture, paste it, and then bam. This is a more physical way of doing it. The first example, I would say that's a mathematician would do it. So doing this. So this is method 2. Method 2. Now, in this frame of reference, this angle is no longer 60. This angle is 30 degrees. And the acceleration is no longer vertical. The acceleration is at an angle. And this angle is 30 degrees. 30 degrees. So my velocity is 20 cos 30 and 20 sine 30. And my acceleration is minus 10 times sine 30 and minus 10 times cos 30, because I'm splitting into components. My initial position is 0, 0 still. And the acceleration and the equation becomes r of t is 0, 0 plus 20 cos 30. So it's 10 root 3, 10 times t, and plus 1/2 multiplied by minus 10 times 30, so minus 5, and 10 cos 30, it's minus 5 root 3 multiplied by t squared. And solve for y equals 0, because y equals 0 at this position. Solve for y equals 0. And it turns out, if you write y is equal to 0 plus 10t plus 1/2 multiplied by minus 5 root 3 t squared, it's going to be 20. T is 20 divided by 5 root 3, which is 4 root 3 over 3. I haven't messed it up. Okay, and then you find the distance. substitute sub t equals 4√3/3. And then you get r of 4√3/3, and it gives you 0 and 80/3 meters. So the distance is 80/3. So this the second method is honestly easier in terms of calculations, but it honestly we use it a lot. We use it a lot. Why isn't what is the acceleration? Because now the acceleration is no longer vertical. Wouldn't you take 30 degrees to the slope? Yes, 30 degrees to the slope. Yes, because this is 60. This is 30. And this is 60. So this makes it, this is 30. So 30 degrees to the slope. So this is 30 degrees. This is my slope. The x-axis is my slope. As I said, my x-axis goes along the slope, and this is a very common thing to do. When you have a slope, what do we have? A slope physics. Image. Like forces on a slope. What we do is we say, okay. Oh no, don't look to background. We say, okay, I want to have my x-axis going along the slope. My x-axis along the slope. My y-axis is 90 degrees to that. Okay, this is my y-axis. My acceleration is vertical. It's like this. Acceleration, g. Okay, so what you do then is you take this, copy, just make it easier for yourself. Up, and then bam. And now you have your x and y axis. Yeah. So the box is now moving along the x-axis. And then acceleration is no longer, the acceleration now has components. It has a component in this direction and a component in this direction. So if this is theta, this is g cos theta, and this is g sine theta. And yeah, so it's like does it make a difference whether you're on a slope and there's gravity, or the gravity is not? Well, I don't know. Yeah, I'll have to finish here because I have to go. And yeah, so enjoy. I hope it was useful. If you are still confused, do watch the old videos because they I think I've tried to make them easier than this one. If you're still confused, okay. So enjoy assignment 2. We will send you emails whether you're in or not by the end of this week. At least we'll do everything possible to do that. Okay. You're welcome. See you.